There is a place on this planet where the ocean stops feeling like water and starts behaving like weight. Out in the western Pacific, far from any continental coast, the surface looks calm, almost empty. Ships cross it every day without seeing anything unusual. But beneath that ordinary blue lies the deepest cut in Earth's crust that humanity has ever found, the Mariana Trench. From orbit, it appears as a narrow, curved shadow on seafloor maps, a long arc that runs for more than 2,000 kilometers, roughly parallel to the Mariana Islands. It is not a single round hole, but a crescent-shaped wound, where the enormous Pacific plate is being forced down beneath the smaller Philippine sea plate. This is a subduction zone, where the cold, dense oceanic crust bends downward and begins its slow descent back into the mantle. The trench is the surface trace of that descent. At most points along this arc, the seafloor lies several kilometers below the surface, already far deeper than any human freediver will ever reach. But near its southern end, something extreme happens. The trench floor drops into a slot-shaped valley carved even deeper into the bending plate. This is the Challenger Deep, the deepest known point in all of Earth's oceans. If you could lift Mount Everest from the Himalayas, invert it, and sink it into this abyss, its summit would still drown under more than 2 kilometers of water. The depth of the Challenger Deep has been measured multiple times using sonar and pressure sensors, with modern estimates clustering around 10,920 to 10,935 meters below sea level, depending on the methods used and the exact spot measured. At that depth, the pressure is more than 1,000 times higher than the air pressing on your skin at sea level. Each square centimeter of any object is squeezed with the equivalent weight of more than a metric ton of water. Under those conditions, spaces filled with air collapse, metals deform, and most machines humanity has ever built would be crushed long before reaching the bottom. And yet, in this hostile zone, there is life. Microbes cling to grains of sediment. Shrimp-like amphipods scavenge on the seafloor. Organic matter filters down from the bright surface world above and is broken apart, reassembled, and recycled in darkness. The deepest place on Earth is not empty. It is simply adapted to rules that human bodies cannot survive. For most of our history, we did not know any of this. Sailors sensed the power of the ocean at its surface, but the shape of the seafloor below was a mystery. Depth was a guess, not a measurement. That began to change in the late 19th century, when a British research vessel named HMS Challenger went to sea. Between 1872 and 1876, Challenger sailed around the globe, lowering weighted lines into the water to probe its depth, collecting samples, and laying the foundations of modern oceanography. Southwest of Guam, the crew measured a depth that exceeded 8,000 meters, a value that stunned scientists of the time. The ocean, it turned out, was not just deep, it was unimaginably deep. The trench that would later carry the name Mariana had not yet been mapped in detail, but that single set of measurements was enough to rearrange our sense of the planet. The expedition showed that beneath the rolling surface was a three-dimensional landscape of ridges, plains, basins, and trenches, as dramatic as any mountain range on land. Over the following decades, technology transformed our view of that landscape. Weighted lines gave way to echo sounding, pulses of sound sent downward, bouncing off the seafloor and returning to the ship. By measuring how long the echo took to come back, oceanographers could estimate depth far more quickly and safely. As survey ships crisscrossed the Pacific, a picture slowly emerged. Off the Mariana Islands, soundings revealed a long, narrow depression deeper than anywhere else measured. As techniques improved and multi-beam sonar systems painted high-resolution images of the seafloor, the outline of the Mariana Trench became sharper. and the location of its deepest valley, Challenger Deep, became clearer. But knowing that the trench existed on charts and actually going there are two very different things. To appreciate what makes the Mariana Trench such a brutal destination, you have to think in numbers, not just images. At the ocean surface, you live under one atmosphere of pressure, about 1 bar, caused by the weight of the air above you. At a depth of 10 meters in seawater, the pressure is roughly 2 bars. One from the atmosphere, one from the water. At 100 meters, it is about 11 bars. Recreational divers seldom go beyond 40 meters, where nitrogen begins to alter the mind and the margin for error shrinks. At 1,000 meters, the pressure passes 100 bars. No human body can survive there without a rigid protective hull. At the bottom of the Challenger Deep, the pressure reaches around 1,086 bars. That is the equivalent of more than 1,000 kilograms of force on every square centimeter of a surface. Under that kind of load, ordinary engineering rules are not enough. Tiny imperfections that would not matter at the surface can become fatal weaknesses. Air-filled cavities collapse. Electrical connectors are stressed in ways they were never designed to be. Even water itself is different. Under full ocean depth pressure, seawater is compressed by almost 5% compared to its volume at the surface. The abyss is denser, heavier, more unforgiving. Temperature shapes the trench environment as well. Sunlight only penetrates the upper few hundred meters of the ocean. Below that, light fades into twilight, then into blackness. By the time you reach the hadal zone, waters deeper than 6,000 meters, the temperature is just a few degrees above freezing, typically around 1 to 4 degrees Celsius. There is no day or night cycle, no visual horizon, only darkness and the occasional flash of bioluminescent organisms. If you could descend through the water column above the Mariana Trench, you would cross invisible boundaries that oceanographers divide into zones. First, the epipelagic, the sunlit surface layer where most photosynthesis happens. Then, the mesopelagic, where light dwindles and many animals migrate vertically each day. Below that, the bathypelagic, the midnight zone, extends down to about 4,000 meters. Then, the abyssopelagic, down to 6,000 meters. And finally, the hadal zone, named after Hades, the underworld of Greek myth. This is the domain of trenches like the Mariana. For a long time, many people assumed that such depths must be almost lifeless. Cold, dark, starved of light, and under crushing pressure, the hadal trenches seemed like biological deserts. But as instruments reached deeper, that assumption began to crumble. Sediment samples taken from the trench floor revealed active microbial communities, not just dormant spores. Some bacteria recovered from Challenger Deep sediments show extreme adaptation to pressure, with cell membranes and proteins tuned to function where other organisms would be torn apart. Amphipods, small crustaceans resembling shrimp, have been filmed and collected in traps at the bottom, feeding on organic particles that drift down from above. Analyses of dissolved organic matter in Challenger Deep sediments have shown that the trench acts as a funnel for carbon and nutrients from the upper ocean. Material that dies and sinks in shallower waters can be transported by currents and topography into trenches, where it accumulates and is processed by deep living microbes. The deepest point on Earth is, in chemical terms, connected to the entire ocean above it. More unsettling is the discovery that even here, far below the surface, signs of human activity appear. Studies have detected pollutants such as persistent organic contaminants and microplastics in the tissues of hadal organisms and in deep trench sediments. Even in the place furthest from human lungs, traces of our industry accumulate. The message is stark. The horizon of our impact has already passed the deepest seafloor. If the trench is a natural frontier, then the question that haunted generations of explorers was simple. Could anyone actually go there and come back? The answer, for a long time, was no. We could measure the depth from the surface. We could lower instruments into the darkness. But sending people required something new. That something arrived in the form of a strange hybrid vessel called a bathyscaphe. In the mid-20th century, Swiss engineer Auguste Piccard developed a design that looked almost surreal. A large float filled with gasoline, chosen because it is lighter than water and relatively incompressible, with a heavy, spherical steel capsule slung beneath it for the crew. The idea was simple in principle. The float provided buoyancy, the sphere provided protection, and ballast weights could be released to return to the surface. On January 23, 1960, a refined version of this design, the bathyscaphe Trieste, made history. On board were Auguste Piccard's son, Jacques, and United States Navy Lieutenant Don Walsh. Their target, the bottom of the Challenger Deep. The dive began near dawn in calm seas near the Mariana Islands. As the ballast tanks were flooded and the heavy sphere began to sink, the world above grew smaller. The surface disappeared. The water outside the viewing port darkened into a uniform green, then black. The descent took almost 5 hours. As they went deeper, the external pressure on the crewsphere climbed past hundreds of bars. The structure creaked and groaned as metal responded to the load. At one point, around 9 kilometers down, a loud bang echoed through the craft. Later, analysis suggested that an outer acrylic window in a small exterior structure had cracked under stress. The inner steel sphere remained intact, but for a moment, the two men were not sure. They made a decision that defines exploration. They continued downward. When Trieste finally reached the seafloor, the depth gauge settled near 10,916 meters, though later recalculations would adjust that number slightly. Outside the port, they saw a fine, light-colored sediment that billowed up like smoke as the craft disturbed it. Visibility was limited. The lights revealed only a pale, muddy seafloor fading into darkness. They reported seeing what looked like a flatfish, a detail that sparked debate for decades, because later research suggested that such fish might not be able to survive at those pressures. Whether it was a fish, a different organism, or simply an illusion created by the movement of sediment remains unclear, but the core fact did not change. Humans had reached the deepest seafloor on Earth and returned alive. They stayed on the bottom for only about 20 minutes before releasing ballast and beginning the long ascent back to the surface. When Trieste emerged, the world's media hailed the achievement. For the first time, the idea of the Mariana Trench shifted from an abstract number to a place human beings had actually visited. And then, for more than half a century, no one went back. The ocean is full of difficult places, and funding for extreme depth exploration is rare. The Cold War moved on. Space programs consumed public imagination. Other scientific priorities took over. The trench remained where it had always been, but for decades, no manned vessel returned to the Challenger Deep. Unmanned probes and sonar surveys continued to refine our understanding, but the human presence vanished. In a sense, that long silence made the trench feel even more remote. We had touched the deepest seafloor once, then backed away. The deepest place on Earth became, again, a rumor of depth rather than an active frontier. But the story was not finished. The planet rarely allows interesting boundaries to stay untouched forever. One day, more than 50 years after Trieste, a new kind of submersible would slide into the waters above the trench. It would be smaller, more maneuverable, packed with modern cameras and sensors, and designed to dive repeatedly to full ocean depth. The age of one-off descents would give way to something different. systematic exploration of the abyss. Before we reach that part of the story, though, we need to understand one more thing: why the Mariana Trench exists where it does, and what it tells us about a planet that is constantly rebuilding itself from the inside out. To see why the Mariana Trench exists at all, you have to zoom out from the abyss and look at the planet as a whole. The Earth's crust is not a single unbroken shell. It is a mosaic of rigid plates floating on the slowly convecting mantle beneath. These plates move a few centimeters a year, colliding, sliding past, or pulling away from one another. In the western Pacific, the enormous Pacific Plate is moving roughly westward, while the smaller Philippine Sea Plate lies to its west. At their boundary, the heavier, older Pacific Plate is forced down beneath the Philippine Sea Plate in a process called subduction. The line along which this descent begins is marked at the surface by a trench, a long, narrow depression where the seafloor bends downward. That trench is the one we call Mariana. Subduction zones are among the most powerful engines of geology on Earth. As oceanic crust is pushed into the mantle, it heats up, dehydrates, and helps generate magma that can rise to feed volcanic island arcs. In the case of the Mariana system, that arc includes the volcanic islands that curve roughly parallel to the trench. Deep earthquakes, some hundreds of kilometers below the surface, trace the path of the sinking plate as it descends. The Mariana Trench and its companion, the Mariana Island Arc, are parts of this integrated system. Trench, descending slab, volcanic arc, and deforming plates all tied together. The extreme depth of Challenger Deep is a local expression of that broad process, where the bending of the plate and the shape of the overriding crust combine to create a particularly deep pocket on the seafloor. In technical literature, scientists use the trench to study all kinds of processes: how oceanic crust evolves as it heads towards subduction, how sediments are scraped off and accreted, how fluids move and influence earthquakes, how the geometry of the slab changes with time. But for most of us, the key idea is simpler. The Mariana Trench is where the surface of the planet folds inward. It is a place where the ocean floor itself is on its way down, into a deeper interior world we can never visit directly. That alone would make the trench interesting. But what draws people back to this place again and again is something more primal, the human urge to go to the limit, to find out what happens at the far edge of the possible. The Challenger Deep is one of those edges. After Trieste's historic 1960 descent, that edge remained untouched by human presence for generations. Other deep dives took place in different parts of the ocean, but no one repeated a manned mission to full ocean depth. The area above the trench became busy in other ways. Surface ships mapped it. Satellites refined our understanding of sea surface height and gravity. Unmanned landers and instruments were deployed to study the water column and seafloor. But the idea of a human being sitting once again at the deepest point in the ocean remained theoretical. Building a new, full ocean depth submersible in the 21st century required money, patience, and a willingness to accept the risk of failure in a very public way. One person who took that risk was filmmaker James Cameron. Known for his work on films like Titanic and Avatar, Cameron also had a long-standing interest in deep-sea exploration. Working with a team of engineers and scientists, he helped design a one-man submersible called Deepsea Challenger. Unlike Trieste, which was shaped like a large horizontal balloon with a sphere beneath, Deepsea Challenger was built as a tall, narrow, vertical vehicle. Its slender profile was intended to reduce drag and allow a faster descent. On March 26, 2012, Cameron piloted Deepsea Challenger to the bottom of the Challenger Deep. The dive took roughly 2 hours and 36 minutes. At depth, he spent several hours on the seafloor, filming in high definition and collecting geological and biological samples before ascending. From inside his small pressure sphere, the view was dominated by sediment, fine, pale, mud-like material covering the bottom, shaped into ripples and small structures by currents. The lights from the submersible cut through water that had not seen sunlight in geological timescales. The environment was quiet, still, and almost abstract, a flat plain under unimaginable pressure. Cameron later described the experience as traveling to another planet and coming back. The equipment performed well, but the dive also highlighted how technically fragile operations at that depth are. Every component must work. There is no quick rescue in the event of a serious failure. At nearly 11,000 meters, you are further from the surface in terms of practical reachability than astronauts in low Earth orbit. Even more radical than Cameron's mission was the next step: the development of submersibles designed not just for one triumphant dive, but for repeated operations to full ocean depth. Among these, one of the most important is a vessel called DSV Limiting Factor, part of the privately funded 5 Deeps expedition. Unlike Trieste or Deepsea Challenger, which were one-off vehicles, Limiting Factor was designed to be reusable. Its titanium pressure sphere is rated for depths beyond the bottom of the ocean, allowing multiple descents to trenches around the world. During the 5 Deeps expedition, which ran from 2018 to 2019, the submersible completed dives not only to the Challenger Deep, but also to the deepest points of the Atlantic, Indian, Southern, and Arctic Oceans. In the Mariana Trench, Limiting Factor made several dives to Challenger Deep, including missions with different crew members and scientific goals. That repetition matters. It shifts the Challenger from a one-time stunt to a place with potential for systematic research. It means scientists can think about long-term experiments, repeated sampling, and monitoring of change instead of just a single snapshot. Other nations have developed their own full ocean depth technologies. Chinese researchers have used a hybrid underwater vehicle called Haidou-1 to explore the Challenger Deep and collect data down to 10,908 meters. These systems, along with autonomous and remotely operated vehicles, form a growing toolbox for hadal science, the study of Earth's deepest ocean zones. As the ability to reach the bottom improved, the focus began to shift from simply "how deep is it?" to "what exactly is happening down there?" That question has several answers, depending on which part of the trench you look at. At the geological level, researchers have examined samples of basalt and other rocks from near the trench and the subducting plate, discovering clues about the age and origin of the oceanic crust being consumed. The Challenger Deep region overlies oceanic crust that formed in the early Cretaceous period and carries geochemical signatures similar to Indian-type mid-ocean ridge basalts, even though it lies in the Pacific Basin. These details help refine our understanding of how plates move and how ancient oceans were configured. At the physical oceanography level, scientists have deployed moored instruments to measure currents, mixing, and water mass properties within the trench. The steep, narrow shape of trenches influences how dense water flows and mixes, making them important sites for understanding deep ocean circulation and the fate of heat and salt at great depths. But perhaps the most surprising trench discoveries belong to biology and chemistry. When core samples are taken from Challenger Deep sediments and brought back to the lab, they are anything but inert. Microbial communities extracted from those samples have been studied using genomic and biochemical tools, revealing organisms with streamlined genomes and metabolic capabilities finely tuned to life under extreme pressure and low temperature. Some strains show evidence of genome reduction, an evolutionary pattern where unnecessary functions are lost over time, leaving a more compact set of genes suited to a stable, specialized niche. In the case of certain hadal bacteria, that niche is the high-pressure, low-energy environment of deep trench sediments. These microbes participate in breaking down organic matter that sinks from the surface and in transforming chemicals within the sediment pore water. Studies of dissolved organic matter in Challenger deep sediment pore water indicate complex molecular assemblages and active cycling of carbon, suggesting that even at nearly 11 kilometers depth, the seafloor is a chemically dynamic place. Experimental work has revealed extremely barophilic bacteria, organisms that not only tolerate high pressure but require it. When brought to the surface and depressurized, some of these strains do not function properly unless the pressure is restored in high-pressure culture systems. This reminds us that normal is relative. For life adapted to the hadal world, the gentle conditions we enjoy at the surface are just as foreign as the abyss is to us. At larger scales, amphipods and other invertebrates live and feed on the trench floor. They are scavengers, picking apart organic fragments that drift down or are transported by currents. Chemical analyses of these animals have delivered one of the most unsettling findings in deep ocean research: contaminants associated with human activity. Persistent organic pollutants, including industrial chemicals manufactured and released at the surface, have been found in the bodies of amphipods collected from hadal trenches like the Mariana. Even microplastics, tiny fragments of plastic debris, have been detected in sediments and organisms at extraordinary depths. This means that materials from our packaging, textiles, and industrial processes are now present in the deepest seafloor ecosystems on the planet. The idea that the trenches are isolated or untouched is no longer defensible. They are connected to the rest of the ocean, and through it, to us. Seen in this light, the Mariana Trench stops being just a curiosity and becomes a mirror. It reflects not only the extremes of Earth's physical environment, but also the extent of our influence. Our waste has reached the same frontier that our bravest machines barely touch. And yet, for all the data we have collected, the trench remains largely unknown. The total floor area of the Challenger Deep is small compared to the global ocean, and only a tiny fraction of it has been seen in detail. Each dive, each core, and each high-resolution sonar swath reveals more complexity. Small landslides on the trench walls, curious patterns of sediment deposition, variations in biological communities with depth and location. Even the exact deepest point is not a fixed, simple spot. Different basins within the Challenger Deep region have depths within a few meters of one another. Measurement uncertainties, differences in reference datums, and natural changes can all influence which number appears in a given table or headline. Instead of a single pit, it is more accurate to picture a cluster of extremely deep depressions, any one of which would still qualify as the deepest place we know. In documentary terms, this ambiguity is a gift. It lets us tell a more honest story, one where the planet is not a solved puzzle, but a system we are still learning to read. There is also another, more subtle boundary at work in the trench story: the boundary between how scientists talk about this place and how the public imagines it. In popular culture, deep ocean stories easily drift into horror. Crushing blackness, unseen creatures, loneliness, and the sheer alien quality of the environment all invite fear. In that sense, the Mariana Trench plays a similar role in the modern imagination as the underworld did in ancient myth. It is the downward direction taken to an extreme, the place where below stops being metaphor and becomes a physical limit. But when you look closely at the real data, the story of the trench is not one of monsters. It is a story of adaptation, physics, slow geological change, and the remarkable ability of life to exploit even the narrowest windows of possibility. Microbes adjust their membranes. Crustaceans reinforce their shells. Engineers thicken hulls and polish welds. Pilots train to sit calmly in tiny spheres while thousands of meters of water press around them. In all of these cases, the same pattern appears. Something pushes against the limit. That is the deeper theme linking the dives of Trieste, Deepsea Challenger, and Limiting Factor. The microbial strain isolated from Challenger deep sediments, the amphipod carrying a chemical signature of human industry, and the tectonic plates grinding down into the mantle. The trench is where limits are tested, by geology, by biology, and by us. We have now reached the point in the story where the Mariana Trench is no longer simply the deepest place. It is a specific physical system with a history, a set of dynamic processes, and a growing body of human interaction. We have mapped its outline, descended to its floor multiple times, and begun to understand some of its secrets. We have also left our mark on it in ways we did not intend. What remains is to ask what the trench means beyond its physical facts. Why does it fascinate us so much? What does it reveal about the relationship between exploration, risk, and humility? And what does it say about a world where even the most remote places are now part of our story? Those questions belong to the final part of this journey. The deeper we go into the Mariana Trench, the more it forces us to ask what deepest really means. On paper, it looks simple. The Challenger. Deep is the deepest known point in the world's oceans, around 10,920 to 10,935 meters below sea level. The Kola Super Deep Borehole is the deepest human-made vertical hole in solid rock, reaching 12,262 meters beneath the surface in Arctic Russia. The Mponeng gold mine in South Africa descends roughly 4 kilometers underground, making it the deepest operational mine on Earth. Krubera Cave in the Caucasus drops over 2,190 meters from its highest entrance, making it the deepest known cave system. Each of these numbers claims a kind of record. Each represents a frontier: deepest ocean water, deepest drill hole, deepest mine, deepest cave. But the more you compare them, the more you realize that deepest is not just a measurement. It is a relationship between humans and their planet. The trench is the deepest place nature has carved into the ocean floor. Kola is the deepest place we have punctured on land. Mines and caves are places where we descend into the crust with our own hands and ropes, living and working in spaces beneath the surface. The numbers differ, but the emotional reaction is similar. At a certain point, depth stops feeling like distance and starts feeling like separation. The deeper you go, the more it feels as if you are leaving our world and entering another one. The Mariana Trench pushes that feeling further than any other place on Earth. Part of that has to do with what the trench looks like, or rather, what it doesn't look like. At the bottom of the Challenger Deep, there are no dramatic rock arches or glowing vents in most of the images and reports. There is quiet, fine sediment, scattered stones, small burrows, and the occasional creature moving in and out of the camera's beam. It is not a fantasy landscape. It is a realistic one, stripped down to the simplest shapes of gravity and deposition. In a way, that makes it more unsettling. We are conditioned by fiction to expect spectacle at extremes: towering structures, giant monsters, visual drama. What the real trench gives us is something else, an environment that feels almost minimal, and yet is physically more extreme than anything we encounter on land. The pressure is crushing. The darkness is absolute. The temperature is near freezing. The isolation is total. Still, the basic elements of an ecosystem are there: energy, nutrients, organisms, chemistry, and time. The trench shows us that life does not need comfort to exist. It only needs opportunity. The trench also shows us something uncomfortable about ourselves. When researchers tested trench amphipods in sediments, they did not find a pristine world beyond our reach. They found plastic. They found industrial pollutants. They found chemical signatures of our age. In 2019, explorer Victor Vescovo reported seeing a plastic bag and candy wrappers at the bottom of the Mariana Trench during one of his dives. Other studies have found microplastics in hadal waters, with samples from the trench containing thousands of tiny plastic pieces per liter in some locations. Deep-sea organisms have been found with synthetic fibers and fragments in their stomachs. The deepest place on Earth is now also one of the deepest sinks for our waste. That fact changes how we tell the story. The trench is no longer just an alien world that we struggle to enter. It is part of a connected system that we have already changed, often without understanding how. When you put all of this together, plate tectonics, subduction, extreme pressure, specialized life, human exploration and pollution, you start to see the Mariana Trench not as a single fact to memorize, but as a lens. Through it, you can see the entire Earth differently. You see a crust that is restless, recycling itself over tens of millions of years as oceanic plates form at ridges, travel across basins, and dive back into the mantle at trenches. You see an ocean that is not just a surface and a depth, but a layered structure with currents, stratification, and hidden highways of nutrient transport. You see life that is not designed for a single environment, but constantly inventing new solutions to new pressures. You see a species, our own, that has developed the technology to go almost anywhere, and the capacity to leave traces of itself even where it never intended to go. In that sense, a dive to the Mariana Trench is not just a voyage downward. It is a cross-section of the Anthropocene. It shows in one vertical line the reach of our curiosity and the reach of our impact. At the surface, ships and satellites capture images, send data, and guide navigation. In the mid-depths, fishing gear drifts, sometimes lost, sometimes abandoned. In the open ocean, plastic fragments ride currents, break down, and sink. In the deep zones, carbon from our activities above eventually finds its way into sediments. At the bottom, in an environment no human body will ever directly inhabit, animals carry our signatures in their tissues. The question then becomes, what do we do with that knowledge? For scientists, one answer is to keep studying the trench as a natural laboratory. Somewhere, they can investigate how matter behaves under high pressure, how life adapts to extremes, and how global cycles of carbon, nitrogen, and pollutants play out in the deepest sinks on the planet. The hadal zone is likely one of the largest long-term repositories for microplastic debris, with unknown consequences for ecosystems and biogeochemistry. Understanding those consequences is not a luxury. It is essential to understanding the future of the ocean. For engineers and explorers, another answer is to refine the tools that make repeated, safe, and precise dives possible. Every generation of submersibles learns from the last. Hull materials improve. Battery systems advance. Control interfaces become more robust. The goal is not just to say, "we went there," but to build the equivalent of research stations that can return again and again. For the rest of us, there is a more personal answer. The trench can act as a kind of compass for humility. We live our lives near the surface of a planet whose interior we barely understand. We build cities, launch satellites, and send robots to Mars, while still not having seen most of our own seafloor. The Mariana Trench is a reminder that unexplored spaces do not only exist in outer space, they exist beneath our feet, in the parts of Earth that are hardest for us to reach. When we look at the trench, we are seeing both directions at once, down into the Earth and forward into our own unknown future. there is also something quietly radical in the idea that the most extreme environment we know on Earth is not dead. It is alive. Microbial communities, scavenging crustaceans, and possibly other organisms yet to be discovered. Life has occupied a place that is dark, cold, high pressure, and distant from all of our comforts. It has taken that challenge and turned it into a niche. That insight stretches our imagination for other worlds. When we think about subsurface oceans on icy moons like Europa or Enceladus, we sometimes picture them as sterile unless proven otherwise. Yet, on our own world, water under crushing pressure and near freezing temperatures, in total darkness, holds active ecosystems. The trench, in that sense, is a test case for our expectations about life in the universe. But even if you ignore the astrophysical implications and stay here, on Earth, the trench still has one more message. It says that exploration is not just about planting flags or setting records. The dive of Trieste in 1960, James Cameron's solo descent in 2012, the missions of Limiting Factor and Haidou 1 in recent years, these are not simply adventures, they are acts of calibration. Each one tells us, in a very concrete way, how far we can push our materials, our designs, and our courage before the environment pushes back. And the environment always pushes back. At Kola, the limiting factor was temperature and deforming rock. In the Mariana Trench, the limiting factor is pressure and the difficulty of building systems that survive it over and over again. In deep mines, it is heat, rock mechanics, and economic cost. In caves, it is geology, water, and the fragility of human bodies in narrow vertical spaces. In every case, the world is setting terms. We negotiate with it using steel, titanium, compressors, ropes, code, and training. But the world is the one that ultimately decides where the line is drawn. The Mariana Trench is one of the clearest and sharpest of those lines. So, what does it mean finally to go inside the Mariana Trench? It means more than descending a machine to a set of coordinates and reading off a depth. It means engaging with all of these layers at once. Geology bending, water compressing, life adapting, humans pushing, and pollution spreading. It means recognizing that the deepest place on Earth is not an isolated curiosity, but a node in a global system that reaches from the upper atmosphere down into the mantle. When a submersible settles on the floor of the Challenger Deep, the scene is deceptively simple. A patch of sediment, some scattered stones, perhaps the shadow of an amphipod passing through the light. Yet, in that small frame, you are seeing the intersection of plate tectonics, ocean circulation, evolution, engineering, and human history. All of those stories meet there, in silence, under the weight of 11 kilometers of water. If the Kola Super Deep borehole is a testament to how far we can drill downward into the crust, the Mariana Trench is a testament to how far the planet itself can shape its own surface downward into the ocean. One is an expression of human ambition. The other is an expression of Earth's own restless dynamics. Together, they define a vertical axis of mystery that runs from the Arctic rock beneath Russia to the underwater trench east of the Mariana Islands. We live our entire lives along that axis without ever feeling most of it. Almost everything we do happens within a few hundred meters of the surface. Yet, deep below us, plates slide, trenches form, sediments accumulate, microbes metabolize, and the ocean quietly rearranges heat and salt over distances and timescales we rarely consider. The function of a good documentary is not just to show these facts. It is to give them weight in the mind, to make you feel, if only for an hour, that the planet you stand on is larger, stranger, and more finely balanced than you thought. The Mariana Trench does that effortlessly. It does not need legends of monsters or underwater civilizations. Its reality is already enough. there's a scar on the seafloor where one plate dives beneath another. At the bottom of that scar, nearly 11,000 meters below us, the pressure is so intense that a human body would be flattened in an instant. And yet, on that same seafloor, microscopic cells continue to divide, chemical gradients are exploited, and small animals search for food. Somewhere in that darkness, plastic fibers drift. Somewhere in that darkness, the hull of a submersible trembles under load. Somewhere in that darkness, the crust is moving, millimeter by millimeter, toward its eventual destruction in the mantle. The deepest place on Earth is not a single story, it is a crossroads. And in the brief moments when our lights reach it, it reflects us back,